Yes, how's you feeling with statics metro? I think it's going good. As a me, it's still a D, but I have no holding. I got like a D. It's like, it was good. I actually really like him. Huh? I can't remember his name, but I think he's a really good dancer.
Yeah, I think I'm gonna go ahead and get started here and welcome to another new week. I guess this is about halfway through. Uh, from August to December, we're right smack dab in the middle of October. I hope that you guys are hanging in there. I know your classes are probably keeping you really busy. It's kind of just go, 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 go. It's not much break these days, but one day at a time, we're gonna get there. I promise. Anyway, welcome. I have a couple of quick announcements here before we jump in today with what we're gonna do. First of all, I'm gonna tie my shoes before I trip on them. Um, I really appreciate all of you guys taking the time to watch that video for me over the weekend. I know it was a little long. Don't worry, I'm going to chop it down today. We're going to review it again. Now that you've seen it once and taken some notes on it, we'll be able to focus on examples and kind of hopefully guide you a little bit towards the homework that's going to be coming up this week on that stuff. So thank you very much for doing that. You will get extra credit for the upcoming midterm for sending those notes in for me. And I'll check those off probably later today. The other announcements are really just about homework. So there's some homework that's due tonight. I see quite a few problems listed on the side board over there. I'm going to try to do pretty much all of those problems and maybe even some more if there's other questions that come to mind. So we'll try to do some of them in class today, but I have office hours, as you know, later on. Feel free to stop by and hang out, and I'll do what I can to help you out. There is also going to be an assignment due on Thursday. I know that's only 2 days from now. However, some of the problems from Thursday's homework, it's really just one section of problems, and some of those were actually done in the video. And on Thursday, I'm going to obviously take questions on Thursday's homework. So I actually think you almost could get away with putting almost no time into the homework outside of class, because between me helping you with some of them and having watched the video already, I think it'll go pretty quickly. So those are the first two homeworks on tap. There will also be one over the weekend and then one for Tuesday. I think the one probably next Tuesday will again be able to just do it in class pretty much. So I have a feeling that that will be fine, but there is quite a bit to do. I did postpone the homework that was supposed to be due last Thursday is due today. So we're kind of playing a little bit of catch up on that. But again, because you guys watched that video over the weekend, we can spend more time on the homework now. And I think that'll make a big difference. Anybody have any questions about that? Kind of where we're at. Okay, so I want to break this class down into sort of two parts. There's sort of the clean up the leftovers of chapter 4 part that I want to do first, and then I'll come back and pick up with the video material. The video material was from chapter 5. I am going to put my screen down in front of this right now. If you didn't get it all copied, don't worry about it, because I will put the screen back up soon and let you finish writing that down. But I want to get this handout up. Let me see if I can get the website up here. So this is our Canvas page. As you can see, as always, I want to go in there and do this files folder again. And inside of there, well, I have special handouts. And occasionally I've been pointing out some things in here. The one I want to have you look at with me right now is the one here that says recap for 4.6, 4.8, and 4.9. At one point, I just decided it takes too long to write it all down on the board every time. So let's just make a handout for it. And so I did that here, and I want to kind of just talk through this again. If you need to, print this thing out and like put it under your pillow for the next 11 nights before the exam so that the information will soak up into your mind. Super, super important summary of the last part of chapter 4, right? So let's just talk through it again, just to refresh our memory. We've got a vector space V, and somebody comes along with a handful of vectors. By now, I hope everybody knows that a basis is the most important concept about vector spaces, and it basically means that the vectors have to span V. That just means they are a spanning set for V. and they have to be Li, linearly independent. So a basis is a spanning set that's also Li. Super, super important. And whenever you have a basis for a vector space, the number of vectors in that basis is called the dimension. So the dimension of V is just how many vectors are required in order to make a basis for a vector space. Now, assuming that you know what the dimension of V is ahead of time, which we don't always know, but if we happen to know what vector space we're working with and what its dimension is, such as Rn would be a good example of that. We know the dimension of Rn is, what is it again? N, right? We know that ahead of time. The dimension of Pn of R, does anybody remember what that one was? N plus 1, right? So that's a good number to remember as well. I think last week we wrote down these dimensions of these very familiar universes, and I sort of said, yeah, it'd be kind of good to know these cold, right? So if we know what the dimension of our vector space is, and somebody comes along with k vectors, and they hand us k vectors, then we can compare the k with the dimension of the vector space. And if k is bigger than that dimension, then you know that you don't have a basis, right? And the reason you don't have a basis is that those vectors must be LD, right? They cannot be LI because it's too many vectors. It's too expensive, right? So if K is too big, then your vectors are not a basis because they are LD. They might span V. We don't really know that until we investigate further, but for sure they are not LI. The opposite scenario, right? That's if K is less than the dimension of the vector space. If I don't give you enough vectors, in that case, there's no chance that they could span V, right? There's not enough of them. You don't have enough vectors there. So they're not going to be a basis because they cannot span V. They might be Li. That's a possibility, but we would have to test that. It's not guaranteed that they would be Li. Right. And then finally, if you do have the correct number of vectors, right? If K is matching with the dimension of V, then your vectors are both or neither. And you can decide whether it's both or whether it's neither in several ways. One way is to just put your vectors into a square matrix, line them up in the columns of a square matrix, and then just use the determinant, right? We talked about that last week. So that if the determinant is not 0, then yes, your vectors are a basis. If the determinant is 0, then they're really going to fall flat. They're going to end up being neither in that case. Okay, so those are the punchlines of the three cases. Let me actually, since I've already started talking about some of the stuff that's relevant for the homework, why don't we take a look at 4.6? There's at least 2 problems on the side board over here. So before I continue talking about the rest of this handout, let's just look at 4.6 really quickly, number 18 and 32. And then I can see if there's any others that people are going to want to ask me about. So on number 18, so this is from the homework that's due tonight. 4.6, number 18. On this problem, they give you the vector space V is the matrices M by N matrices of R. Can somebody remind me what the dimension of this vector space is? M times N, right? And on number 18, they tell you that M is 2 and N is 3. And so we're talking about the dimension of the 2 by 3 matrices. And so using our formula, that would be 6. Okay. And so that's the universe that we're working in here. Now, if you look at this problem, they give you the set S now. They're going to give you some vectors in the set S. And so it's the set of 1, 1, 1, 1, 1, 1. That's the first matrix. These are all going to be 2 by 3 matrices. I won't write them all down, but let me just kind of get the first couple of them up here so you kind of have an idea what I'm doing. There's a couple of matrices there. And the very next thing I would probably want to do is just count how many vectors are in this set S. And so again, I didn't write them all out. But if you look at the problem in the book, you can just count them. 1, 2, 3, 4, 5, 6. There are exactly 6 vectors there. So in this case, for problem 18, the K value matches the dimension of the vector space. So I'm in this third bullet point. And so I already know that these vectors are either both or neither. Both would be a basis, right? Li and spanning set, that's a basis. Otherwise, it would be neither. And so we have to decide that now. And what I had suggested is that you can always take your vectors and lay them right into the columns of a matrix. So you could set up a matrix here, capital A, where the first column would be, 1, 1, 1, 1, 1, 1. And the second column would be 0, -5, 1, -1, 0, 2, and so on and so on. And you would get a 6 by 6 matrix here. And maybe this is the reason that it ended up on my sideboard over here is like, is Dr. Annan really going to make me do a 6 by 6 determinant here? Because if I want to test if this is invertible or not, I'm going to have to do something. I could do EROs as an alternative, or I could take the determinant. Either way, I'm dealing with about as big of a matrix as we've probably seen. And just doing some, what I'll call chapter 2 busy work on it. Is there any shortcut, though, that anybody might have noticed on this problem, Marco?
There was a column where it was just 2, 2, 2, and 2, and they all cancel out except for the first row.
Yeah, so somewhere in the list, I didn't write these all down. There's another matrix in that set, which is 2, 2, 2, 2, 2, 2, like that. And if you didn't notice that, then of course you would be stuck dealing with the 6 by 6 matrix and working it out. But what is the implications? I'm sorry, Marco, I didn't quite get the final punchline of your comment.
You do EROs, so it all cancels out underneath, past the first column, in the first row. So you end up having a free variable.
That's true, but can we just talk about it without doing EROs somehow? Go ahead, Angela.
Basically, you could create an equation that equals 0 based off like if you 2 times the first one.
I think this is the fifth one here.
Yeah, the fifth one.
Yeah, so you can just name your vectors 1, 2, 3, 4, 5, 6, right? And then you could just notice that, so you could just notice that V5 is equal to 2 times V1. That would be considered a linear dependency. So you could just make that observation. Or if you wanted, you could, sometimes with linear dependencies, you try to get everything to one side of the equation. But if you have an equation like this, where you can cancel out some or all of your vectors in a linear combination without putting zeros in front of the vectors, then that means that those vectors are LD. And so you spent $2,000 right here, right, on these 2 vectors, but you really didn't want to do that because you only needed to really have this vector in the set. You can create this one by just taking a scalar multiple of the first one. So these vectors are LD, and if it's a thumbs down on the LI-LD part, then because it's got to be both or neither, it's also thumbs down on the spanning part of the question. And so this one would be neither, right? So I'll just say implies neither based on my little bullet point list here. Yeah, question.
I have a question.
Please.
They happen to be both, like in terms of the exams, do you want us to refer to it as either just both or basis?
I'll probably ask the question, tell me, are these vectors only a spanning set? Are they only linearly independent? Are they both or are they neither? And you just circle the answer.
Okay.
But it is good to appreciate that anytime you're saying it's both, that is a basis. Eduardo?
Kind of going back to like chapter 2, but
Okay.
Can we assume that if we get just a square matrix and we get a column of zeros that the diagonal would be 0, so like the determinant 0?
So it's exactly what would happen if Marco carried out his EROs. He would get a column of zeros at some point. So whatever. Yeah, you might get like a column of zeros here. What I would do, the easiest way to say it now is the determinant of this matrix is definitely 0, because if I did cofactor expansion along that column of zeros, remember cofactor expansion, you'd have 0 times something plus 0 times something plus 0 times something. It would just be 0. And we remember how we do the bookkeeping with the EROs. So if this determinant is 0 and we try to trace back to the original matrix, the determinant of the original matrix will have to also be 0 because none of those bookkeeping effects will change a number from 0 and make it not 0, or take something that's not 0 and make it 0. So you could, I don't know if I'm answering your question, but you could do it that way if you wanted to. Yeah, let's say you didn't notice. It's a reasonable question. What if you didn't notice that, you know, these two vectors were both sitting here as scalar multiples? Then you really would have to kind of get in the weeds a little bit with this 6x6 matrix, do some elementary row operations until you could tell something like this, a column of zeros, or something was more obvious. But you are right that if you went all the way to row echelon form, there would be a 0 somewhere on the main diagonal. And so the determinant would be 0. But that's a lot of work. That's a lot of work. Okay, so it's much better in this case if you kind of just notice the relationship there. Does that help a little bit? Okay, so that's number 18 on the homework. I don't really want to use that board or this one at the moment. Can I erase on this board yet? Is this okay? Let me go ahead. This is a good space to write down number 32 as well, which is also on the board over there. 32, this is a good question. It says, find a basis for the subspace of M2 of R spanned by, and then they give a list of vectors here. 1, 3, -1, 2, and then the second one is 0, 0, 0, 0. The third one is -1, 4, 1, 1. And the fourth one is 5, -6, -5, and 1. Okay, so they're asking you to give a basis for the subspace spanned by these vectors, right? So in other words, the vector space here that you're working with, it's not so much M2 of R. M2 of R is the big universe that everything is living inside of. But this vector space could be just explained as being the span of these matrices. This is what we're looking at, okay? Let's recopy the matrices here again. Okay, and I also am a big fan of this type of problem as well. The question is, find a basis for V. Find a basis for V right here. So we're not finding a basis for M2 of R. We're finding a basis for this guy, right? So this is very different than the problem we just did a moment ago. Because in this case, we're looking at a vector space that we have probably never thought about before. I mean, it's a subspace within the big universe of M2 of R. Of course, we're familiar with M2 of R, but we're probably not familiar with this subspace. We've probably never seen it before. It's just being created as a span. Right, and we do know that whenever we form a span, we'll get a subspace. So that at least is good. And now they want us to find a basis for it. But since we have never seen this vector space ever before, we probably don't know its dimension. We probably don't know how many vectors should be in a basis. If we do not know the dimension of our vector space, then these this bullet point rubric here of like, okay, if K is bigger than the dimension, less than the dimension, or equal to the dimension, cannot be used. You can't use this rubric if you don't know the dimension of the vector space that you're working with. Okay, does everybody understand that? You have to use this rubric, you have to know what K is, and you have to know what's the dimension of the vector space that you're trying to find a basis for. And here, we don't know what the dimension of this is. By the way, please don't just say, oh, there's 4 vectors, so it must be 4-dimensional. That doesn't work either, because after all, what might be wrong with these vectors? They could be LD. They could actually be LD. These were just sort of handed to us out of the sky. We have no idea what kind of vectors these are. They could be really bad vectors for our basis. They are. I will tell you this, though. The one nice thing about a vector space that is created in this way, the one nice thing about a vector space that is created this way is that the vectors that are in the set, they do span V already, which is half of what you need for a basis. Because a set of vectors will always span whatever they span. Okay, I know that sounds a little not like a very deep comment, right? The vectors will span whatever they span. So if you create V as the span of some vectors, then those vectors are already, before you even take a breath, those vectors are already a spanning set for V, because that's how V was formed. It was formed as the span of those vectors. So those vectors are halfway to being a basis before we even take a breath, you see. The only issue is, are these vectors maybe going to be LD? Can somebody remind me, how am I going to test whether the vectors are LI or LD? Audrey?
Put them in the columns of the matrix.
That's the answer to everything in this class. Put these vectors into the columns of a matrix, right? So I'll form a matrix here. I'll call it capital A. The first vector, 1, 3, negative 1, 2. The second vector, 0, 0, 0, 0. The third vector, negative 1, 4, 1, 1. And the fourth vector, 5, negative 6, negative 5, and 1. And what do I augment a matrix with if I'm testing it for LI or LD? Zeros, exactly. So this goes back a couple of sections, but we just augment that with zeros. Okay, by the way, some people already noticed 0, 0, 0, 0 is in the set and decided to just throw it away before they even started writing this down. That's fine. If you recognize that that vector is going to be thrown out eventually, you could just do that up front. But I'm just playing dumb here and saying, well, I don't know. I'm just going to put all the vectors into the columns and just go through the motions of this. So I go ahead and I'm going to spend a moment here to do the EROs. I have my pivot in the first row already. If I take negative 3 times the first row and I add that to the second row, I should get 0, 0, 7, and negative 21, and then 0. And then on the third row, I'm just going to add the first row to the third row. I get all zeros. And then negative 2 times the first row added to the third row, 0, 0, 3, negative 9, and 0. And I can actually see that the bottom row is going to be a multiple of the second row. So if I was to go one more step, that row would also get zeroed out. Notice I'm getting rows of zeros here. I don't really care about rows of zeros. That isn't the main focus of what we're doing. What I really want to focus on, my friends, are the pivots. And in this case, I have pivots in the first column and the third column, which means that the second and fourth columns are going to be associated with free variables, as we talked about before. Yeah, Blake?
When starting the EROs, is it okay to drop the second columns?
Yeah, that's what I was saying a moment ago. If you noticed already that that vector needs to be thrown away and you just do it ahead of time, you certainly can. What you want to have here, guys, if you're looking for a basis, you should not have any free variables in this matrix, because that would be associated with a linear dependency, which we want to get rid of. So what we have to do here, guys, is very simple. It's very simple. We just say, look, the vectors that are corresponding to those free variables, they need to be thrown away. So the second and fourth columns, I need to throw those away. And that basically, in effect, means you're throwing away the second and fourth matrix. And so your answer for this problem, your basis here, should just be the first and third matrix that you have, right? So your answer here, final answer, would just be the set of the first matrix, right? And the third matrix. See, I think everybody can see that we need to throw away 0, 0, 0, 0. Nobody wants to spend $1,000 on that vector. But what's maybe not as obvious just glancing at this is that we actually also had to throw away this fourth vector. Andre?
Could you explain again, like why that whole page isn't relevant to this problem?
It's not really relevant because we don't know the dimension of V. So I don't know, when I first, is there anybody in this room who could look at this set of vectors originally and tell me it was gonna be two-dimensional? If you can, maybe you could take over for me, because honestly, I can't see that, right? I look at this and say, oh, there's 4 matrices there, so maybe the dimension's 4. And I see, oh, well, there's a 0 vector, so probably not. Okay, so maybe the dimension's 3. It turns out it's not, it's actually only 2. But you don't discover that, right, until you actually go through this work here with the elementary row operations. And if you don't know what the dimension of your vector space is, then you don't know what the correct number of vectors is that you should be ending up with for your basis, you see. And so you're kind of flying blind a little bit. This is a vector space we've never seen before. We don't know how many vectors to expect for the basis. And so we're going to just have to kind of go through this process on faith and just get to the answer that way. Yeah. Okay, does this make sense? Any other questions on this one? Gilbert, go ahead.
Why did the fourth column is thrown out?
The fourth one is thrown out because, do you see here where the pivots are?
Yeah.
There is no pivot in this last column. So if I associate it like I usually do, we associate these columns with these constants, right? C1, C2, C3, and C4. Li means all the constants have to be 0. But right now, that fourth column is free because there's no pivot in that fourth column, which means that C4 can be any number that we want, not necessarily 0. And so we don't like that. We don't want that. We have to get rid of the free variables. And a great way to do it is to literally just imagine that we've gotten rid of those columns. If this was the matrix that was in front of us, now we would look at it and say, oh, there's no free variables there at all. That's good. That means the vectors are Li. At least after we've gotten rid of the other 2, we're left with just these Li vectors.
Okay.
Great question.
Thank you.
Yeah, you bet. Anything else here, Audrey?
Kind of about this page, but for K and N, could you explain again, like what are each of those?
Sure. K is just the number of vectors that you're given. So that's usually in the problem it's going to be given. 1, 2, 3, 4, whatever. You just count the vectors. N in this handout refers to the dimension of V, if you know it. If you don't know it, then you can't use this rubric, right? But if you happen to know what the dimension of your vector space is, that's what you can.
It's kind of like the universe, which your basis.
V is actually the vector space that you are working with. So like in this problem, I would say that my big universe is the whole M2 of R. But within that, I have this subspace, right? This is a subspace, but this is actually what I care about right now.
Okay.
And so this is the thing that unfortunately we don't know what its dimension is. And so we can't really use the handout so much. We have to really get going on the ERO calculation.
I see. Okay.
Yeah.
So if like we did know more, or whatever, the M2 bar, like that means kind of nothing.
Yeah,
Okay.
exactly.
Okay.
Exactly. Guys, if you have a study buddy in this class, a partner, somebody you're working with, you can make problems like this so easily just for yourself. You just say, just say, oh, I'm going to take V to be the span of, and then make up whatever you want. 3 minus x squared, x plus x cubed, 1 minus x plus x cubed, 2 plus x, whatever. Make up an, if you don't like your study buddy very well, just make it even harder, put more things in there. But just give them this problem and ask them, oh, find a basis for that. Right? And of course, you should work it out before you give it to them, but you can make up a problem like this. And then, you can remind them that just because there's 4 things in the list here doesn't mean that this is 4-dimensional, right? Because those vectors could be LD. If you want to challenge your study buddy, create some vectors that are LD to begin with, and you put those in here. I mean, this is exactly how I'm going to write my exam, right? I'm just going to think of my favorite vector space. I'm going to grab some vectors. I'm going to form their span, and then I'm gonna ask you something about it. So it's actually something all of us could do. We could create plenty of examples of that. There's gonna be a problem just like this on the review materials for the midterm. So you'll definitely get to see that type of thing. But it's really just this type of homework problem. Okay, great. Is there anything else on section 4.6? I know that I've gone through both of the problems that were listed up there from 4.6, but was there any other, for now anyway, any other problems from that section that people are having some question with? Alex?
I think for 20.
Oh yeah, 24. I'm glad you brought that one up. Let me look at 24 as well. 24 is kind of just a weirdly phrased question, so it tends to throw people off a little bit. But again, on 24, what we have here is so the big universe is R3, right? That's in the background of this problem. But what we really care about is S, which is the set of points that satisfy this equation. I'm just going to write it like this, guys, just to abbreviate the question a little bit. The set of x, y, and z such that x minus 3y plus z is equal to 0. And again, they're just asking for a basis for S. Does anybody have any thoughts about that? Or about how to approach this problem?
It's a null space, so then it's already a spanning set.
Okay, so there's actually two different ways that I've sort of tinkered around with this problem. One of them is you can actually recognize that S is just a null space. I know it looks a little funny because there's only one equation there, but this is literally just the null space of the matrix 1, -3, 1. Like you just have a single row. The matrix only has one row to it. And the coefficients of that left-hand side, which are 1 and -3 and 1, are just laid out into a single row, like so. And so if it's a null space, I hope everybody, well, this is a good time to remind you, if I have a null space of a matrix, how do I find a basis for it? Well, I have to bring the matrix into row echelon form and then bust out the free variables. This matrix is already in row echelon form. We can circle a pivot right there. And I see that my free variables, so these columns, remember they align to the X, Y, Z here. The free variables on this example would therefore be which ones? Y and Z, okay? So I like to change letters, this is my usual habit. I change Y and Z into free variables like so. And then if I solve for X, well, I can just go back to my original equation and solve for X. It's going to be 3y minus Z. Well, that'll be written as 3r minus T. And so there's your, oops, there's an equal sign there. There is your expressions for X, Y, and Z. And so your null space, right? Your null space for S is just the set of 3r minus T, comma, r, comma, T, such that r and T are real numbers. And once you have that, how do you get a basis for it? You bust out those variables, right? So you bust out those variables. I'm going to do this kind of quickly, guys. When I bust out the R, I'll get a 3, a 1, and a 0 out of those slots. And when I bust out the T, I should get a -1, a 0, and a 1. And that is my list, right? You make your list of vectors after you bust out those variables. I've got two things here. And these vectors are a spanning set. Let's just be careful here. When I do the process of writing the form of the vectors, busting out the variables, and making my list, that will give me a spanning set for S. Okay. Technically, if I want to find a basis, these vectors also have to be Li. Is it clear that they are Li?
Yes.
Let's just, I don't know, I'm tired this morning, I'll play dumb again. Let's imagine I don't know that they're Li. I can always take these vectors and lay them into the columns of a matrix, augment it with zeros and do my EROs, and I'll see that there's no free variables. Okay, but there is a little bit of a faster way to just glance at these vectors and know that they are Li already. And that is because there's only two of them. You remember my comment last week? I said at some point that when you only have two vectors, then they are Li unless they are scalar multiples of each other. So I can just look at these and say, yeah, these are not scalar multiples of each other, so they are definitely Li. And so they're a basis. Okay, so this is your basis right here. And what is the dimension of this set? Dimension, just, that's an easy one. It's just how many vectors are in your basis. Well, that would just be 2. That would just be 2. Okay. Make sense? So it turns out this is a null space problem in disguise. It never uses the word null space in the question at all, but you have to recognize that, oh, they gave me an equation that is set equal to 0. That sounds like null space, a setup of a null space problem. Did anybody think of a different way of doing this problem? Just curious if there were any other thoughts about it. I'm definitely happy with this solution. This is great. But just in case, you guys, I think you've all taken Calc 3 probably. If you just looked at this equation, somebody on the street just comes up and hands you that equation, like that would ever happen. But if it were to happen, what kind of an equation is that? Like, what does that remind you of from calculus?
So plane?
Yeah, it's a plane. It is actually the equation of a plane, in fact. And so from that, you might already know that the dimension is 2. Because when you see something that's a plane, a piece of paper, basically, a flat plane, it should be possible to span it with 2 vectors. And of course, it looks 2-dimensional, right? So we would actually suspect, let's say we didn't do the null space approach and we just looked at this and said, oh, this is a plane, right? Then you might already expect ahead of time that since it's a plane, it should be 2-dimensional. Ultimately, that is what we discovered in the first approach as well. But now we're sort of seeing it more from a geometry perspective. Okay, this is physically going to be a plane, and I know the dimension of that would be 2. So we can think of it in those terms. And if we know what the dimension is, that's always helpful. If we knew that ahead of time, if we said, yep, I know it's a plane, and therefore I know it's going to be 2-dimensional, then we know how many vectors should be in our basis. And another approach to this problem, guys, would be to literally just find a couple of points that are on that plane. So I could do, I don't know, I could do 6, 2, 0. I can see that's on the plane. If I plug in x equals 6, y equals 2, z equals 0, it works. Okay. And then I could find another point that's also on the plane. I want 2 points, right? Because it's 2-dimensional. So I could pick a different point, a different vector, in other words, that's on the plane. Maybe I pick, I don't know, 0, 1, 3, just to make something up. And these 2 vectors, they are both in S. They're both on the plane. They are not scalar multiples of each other. And so that would be another basis. That would be a different correct answer. So you could definitely have done that as well. Just make sure if you're gonna grab 2 points, be very careful that the 2 points that you grab are not just scalar multiples of each other. So if you picked 6, 2, 0, that's fine. But then don't follow that up with 60, 20, 0. Because then you've got 2 vectors that are LD. You don't want that. So you have to be a little careful. But as long as the second vector is not a multiple of the first one, that's kind of a cheap way to get the basis here. And just find a couple of points that are on the plane. Okay, good question. Does that help, Alex? Awesome. Anybody else have anything from this section that they want to talk about here today? Okay, well, if you think of things later, we've got office hours that we can take advantage of. Let me scroll down on the handout a little bit here. The bottom half of this little recap handout is also hugely important. This is a summary about null spaces, row spaces, and column spaces that we did last Thursday. And you do want to be kind of getting this into your head a little bit, like what are these different spaces? We already talked about the null space a little bit. The row space is just the span of the rows. The column space is just the span of the columns. Those are both going to be subspaces, but the row space is a subspace of Rn, while the column space is a subspace of Rm. Okay, and then notice the dimensions of these spaces. The dimension of the null space, we call that the nullity of the matrix. That was a new word from last week. The nullity is just the dimension of the null space of a matrix. And the opposite concept is the rank. The rank is the dimension of both the row space and the column space. And these two numbers are very closely related because remember, the rank is just the number of pivots in a row echelon form. The nullity is actually the number of non-pivots. Those are the columns that are giving me the free variables. And if you add pivots and non-pivots together, you better get all of your columns, right? Which would be n columns. So this theorem at the bottom relates the rank and the nullity to each other as a really good thing to know. Okay, so I think that's kind of helpful. In the far right column, how you find a basis for those subspaces. Luckily, to do all three of them, to find bases for all three of these subspaces, you start off the same way, which is that you just simply bring your matrix into row echelon form. Circle those pivots and then kind of go from there. Okay, so I won't go over all of this again right now. It's pretty straightforward how you do these bases for these subspaces. But there is a little bit here you've got to be careful with. Make sure you get the M's and the N's in the right places, the ranks and the nullities in the right places. But as far as an overall summary, this little half sheet is really pretty golden for that. It should keep you hopefully on track. And so then there's some homework about this. Actually, so one other thing. We learned if we have, I'm going to talk about this invertible matrix theorem. We learned that if we have an invertible matrix, right, we knew from way back when that for an invertible matrix, the rank was n. This number was n right here. For an invertible matrix, the rank is n, which of course means that the nullity has to be 0. The null space of an invertible matrix is just 0. Okay. Notice I've got dots here. I've left off some of the statements, but I'm just kind of hitting some highlights here. So the null, if I have an invertible matrix, the null space is like nothing. But we also talked last Thursday that in that case, the row space and the column space are both massive. They're both equal to the same Rn. Keep in mind, there is no M here because the matrix is a square size, so there's just an N. And so the column space and row space, I mean, we've known all along that the column space and row space, they are subspaces of Rn or Rm. But in this scenario, they're not just subspaces of it, right? The column space and row space are not just subspaces of Rn, they are Rm. They are the full big universe that this whole row space and column space were a part of in the first place. So they are massive. I mean, this is always a possibility. You grab a handful of vectors and you form their span. You could get something that's not that interesting. You could get the entire big universe that the problem is living inside of. So you could get that the column space and row space are the full Rn, whatever that big vector space is. So I want everybody to kind of understand that for an invertible matrix, we have a really good grip on what these subspaces are. The null space is just 0. the column space and row space are both the full big universe of the Rn. They're absolutely huge in this case. So there were some other statements that I didn't recopy here in the notes in this recap, but this is some of the highlights. The full invertible matrix theorem is in the back flap of the book. So you're looking for an easy reference to it. You can just find it here. So don't forget that the columns of this matrix will be Li. The rows will also be Li. The columns will be a basis for Rn. The rows will be a basis for Rn. All of these things are true for an invertible matrix. Okay. So with that in mind, I think we can tackle these problems on the board now that are from 4.8 and 4.9. Both of these sections kind of go together. So let me talk about number 17 here from 4.8 with you guys. We'll do this these two problems together right now. So on 17, it says A is an M by N matrix. We have any matrix. So these are both proofs, by the way. These are both theoretical items, but they're both very short. They're both very short. And what it says is that we're going to assume on number 17, we're going to assume that the column space of A is equal to the null space of A. All right, so that's not always true for any matrix, but if we assume here that the column space of A equals the null space of A, then what we are being asked to prove is actually that this is a square matrix. So the M and the N actually do have to be the same here. That's actually what we're going to try to show. And I say prove, it's kind of a strong word. It's really just a one-sentence explanation. It's more than anything else. It's what we need to give here. Does anybody want to give it a try? Anybody have a thought about it? Angela?
I was thinking about using the subspace, what they mean.
Yes.
And like, it's a square matrix.
Exactly, right? See, guys, take a look. The column space, as Angela just said, the column space is a subspace of Rm. I'll just stop right there. That means that anything that is in the column space has M slots, right? The vectors in Rm, they all have M slots. So if I live in the column space and I write down what my vectors would look like, they would have M slots in them. Okay. But then on the other hand, the null space is a subspace of Rn. So anything that's in the null space has to have N slots. Well, how could something with M slots be equal to something with N slots? I mean, have you ever heard of a vector, could you ever imagine saying something like this? Something with 2 slots could be equal to something with 3 slots. It doesn't really make sense. In fact, you would say these vectors aren't even in the same universe. They don't even live in the same world. And so I would not expect that you could ever write, like, this would never be true. Okay, this just wouldn't make sense. Okay, so it's really just that. It's basically exactly what Angela just said. Let me write down an explanation here so my grader can read 30 of these papers all exactly the same. It's totally fine. I don't mind if he chooses to grade this one. So I would probably just say, since the call space of A is a subspace of Rm, and the null space of A is a subspace of Rn, we must have M equals N. That's basically it. So one sentence. Something with M slots cannot possibly be equal to something with N slots unless the M and the N are the same. That's it. Okay, that's 17. Let's do 18. On 18, they're going to give us, this time it's going to be assumed to already be a square matrix in the first place. So n by n. And this time they're going to tell us to assume that the row space of A is equal to, what is it? The null space of A. So assume that the row space is equal to the null space. And the claim is the thing we want to, sorry, prove. Let's write the word prove again. What we're being asked to prove here is A is not invertible. A cannot be invertible. Does anybody think they have a, maybe somebody else have an idea this time about why this would be true? This is also very short. Nathan?
Because for an invertible matrix, the row space of A has to equal 0. The row space has to equal R and N.
Exactly. If the matrix was invertible, look what your null space and row space would have been. Clearly not equal to each other, right? So if I know that the row space and null space of A are the same, then of course that matrix cannot be invertible. Let's just write that down as well. This is another one-liner, right? So if A was invertible, then according to what we wrote over there, the null space of A is just 0. And the row space of A is the full Rn. And clearly, those are not the same thing. Those are not the same thing. 0 is not the same thing as Rn. So the null space and row space would be different. And so from our assumption, I guess I'll write a second sentence here. From our assumption, therefore, A cannot be invertible. If it was invertible, we violate that assumption. That's exactly the point. Blake?
Would it also be a valid proof if we set rank A to equal nullity A?
Yeah, you could do that. If the row space and null space are the same, then their dimensions are the same. Right? So the dimension of this would be the rank of A. The dimension of this would be the nullity of A. And so you would be saying that the rank is equal to the nullity. But of course, we know from this invertible matrix there, I guess it's not explicitly on this list that I have here. But if you go back to the whole list, for an invertible matrix, the rank is n and the nullity is 0. Okay, so those are not going to be the same. Yeah, you can totally do it on the level of dimensions as well. Yeah, very good. What do you think? Is this clear to everybody? A couple quick little theoretical items here. Okay, we got one more to do and then we'll take a little break. Okay, so the last one that, well, at least it's on the sideboard is number 14 from the next section. So let's go to number 14 in section 4.9. And then we'll take a little break. So number 14, this is, I don't know if you guys all conspired to put all the best problems on the board this morning over here, but these are all the ones I would have chosen to talk about. Like these are really good problems to discuss. So in this problem, A is a 3x7 matrix. And again, if you haven't done all of these problems and thought them all through yet, that's totally okay. But just do your best to try to follow along here and make sure you're understanding how this is working. They're going to give us as an assumption that the nullity of A is 4. And they're going to ask us to show that the column space of A is equal to R3. I actually think it's kind of useful since we have the specific size here So to kind of draw it out, so you can kind of visualize it a little bit, I've got 3 rows. Each row has, 7 spaces in it. So this would be the shape of a 3 by 7 matrix. And I can see that, yeah, the columns are all going to have 3 slots in them. Okay. Well, in fact, we know that the column space is a subspace of R3. Now that's a far cry from saying that it equals R3, but at least it's a subspace of R3. Let's start with that. We can at least write that into our solution. So the first observation is, for the solution here, the first observation is note that the call space of A is a subspace of R3. So we can start off with that. It's a subspace of R3. That's not quite as strong as what we're claiming, though. We're claiming that the column space is equal, again, to the full universe of R3. Does anybody have an idea how we're going to get there? You have to get a little bit further than just that we have a subspace. We need to actually get that it equals R3. Yeah, Angela. Exactly. We're going to have to use this nullity thing, right? And the nullity is 4. That has to come into the problem somehow. So this is a 4 right here. What is n on this problem? N is always the second number, so it's 7, right? So n is 7. So I know what the nullity is. I know what n is. So I can actually solve for the rank if I care. If I care, I can solve for the rank. It might be nice to solve for the rank because after all, the dimension of the column space is the rank. So it'd be good to know what that is. So in this case, the rank of A is equal to n minus the nullity of A. And n is 7, and the nullity of A was 4. And when we do that subtraction, we get 3. We get 3. So the rank of this matrix is 3. Oh, so the column space is not just a subspace of R3, it is a 3-dimensional subspace of R3. Right? It's a subspace of R3, and we now know what its dimension is. Its dimension is whatever this rank is, which was 3. So, thus, the dimension of the column space of A is 3, right? And we're being asked to prove something about the column space. So as much information as I can find about the column space, the better. I know what it's a subspace of. I know what universe it lives in. And now look how big it is. Look how big the column space is. It's actually as big as the universe that it's in. So you have a 3-dimensional subspace of R3. There's only one thing that can be, which is the full R3. You can't have something smaller than R3 that is still 3-dimensional in R3. That just doesn't work. So these two observations, let's actually put a little star into our solution here. My grader will be so impressed everybody's got everything labeled exactly right. From those 2 stars, from the star and the double star, right? The column space of A is equal to R3. It's equal to R3. What do you think? Does that make sense? If it's 3-dimensional and it's inside of R3, it must be R3. It can't be anything smaller than R3. If it's smaller than R3, it'd be a plane or a line. It'd be something 1 or 2-dimensional. So, everybody with me? The column space is always good to know what's it a subspace of and what's its dimension. That's kind of what we're using, the two main points we need to make here. There is a follow-up to this question, by the way. It asks us, is the row space of A equal to R3? So just as a follow-up, and we should answer this one as well for the homework. The follow-up is the row space of A equal to R3? Yes. Sorry, who said yes? Marco, do you want to tell me why?
Basically, it'd be the same thing, in respect with the rank, since row space and column space have the same rank, and then just within the same boundaries of.
So-
Are we on the worst?
Okay, so we definitely know that the dimension of the row space of A, according to our handout here, it's also the rank of A, which is 3. We already have all that information. So we're talking about something that's 3-dimensional. Does that make it equal to R3? If something is, it's the correct dimension, but does just having the right dimension mean that it's exactly that same space? I mean, here's something that's 3-dimensional that has absolutely nothing to do with R3. Right? This is a universe of polynomials. Right? So I wouldn't just go off of the dimension. It is the right dimension. But Audrey?
So that's the dimension, but is it in the subspace of 7?
That's the issue, right? The row space is a subspace of Rn, and n is here, right? N is 7. So we have the correct dimension, but so I'll say, so I'm actually going to come back and say this is no, it's because it's a subspace of R7. So row space of A, this is why I wanted to go over this problem. It's a really good conceptual question here, right? This is a subspace of R7. It is 3-dimensional, but that doesn't make it equal to R3. It maybe, for example, if it has 7 slots, maybe it looks like this. Maybe your row space is vectors that look like that. A, B, C, 0, 0, 0, 0. If you bust out the variables on this and write down your list, you'll get 3 things, right? But we wouldn't say that this is equal to R3. We would say that it is a subspace of R7 that has the same dimension as R3. But the word equals, that's a very strong word, right? I wouldn't say that literally this row space is equal to R3. So that's why we would want to say no on that last question. It's a subspace of R7, which is a completely different universe from R3. Right. Marco, are you okay with that? Is that better? Okay. How's everybody else feeling about this? Nathan?
So just to make sure, if the dimension equals like for all space, if the dimension always equals m, then it is m, like it's the it's more one.
So if the dimension of the column space was m, then since it's a subspace of Rm and it's m-dimensional, it must equal Rm.
It is r.
It is Rm. Yeah. It's not I mean, anytime you take the span of a set of vectors, you get some weird thing. You don't know what it is. It's just all possible linear combinations of those vectors, right? But in this case, it turns out that this column space isn't some bizarre thing. It turns out after you take the span of the columns, you actually get every vector of R3. And so it is actually just R3 itself. And you can actually view the columns of A as being a spanning set for R3. So that's a nice way to think about it as well. Oh, here's a question for you. This is not from the homework, just off the top of our head. Would the columns of A form a basis for R3? I see a yes, I see a no, at least one vote in each direction here. Why not, Angela? Yeah, there's 7 columns here, right? You would not expect 7 vectors to be a basis for R3 because R3 is only 3-dimensional. So if I had more than 3 vectors, they got no chance. They're going back to our rubric here. If K is greater than the dimension, then they must be LD. Okay? But of course, those column vectors, they would span R3. The span of the columns does equal R3. So this would be a spanning set. These columns, these 7 columns here, guys, these 7 columns would form a spanning set for R3, but not BLI, because there's too many of them. So they are not a basis. It's a good thing to think about. Okay, well, there's a lot of stuff here, but isn't this nice? Because you guys watch these extra credit videos, we can spend a lot of time kind of hashing out the homework, which I think is great. Let's take a 10-minute break. After the break, I'm going to come back. And if you haven't written down the recap yet, we're going to go to chapter 5 after we take a 10-minute break. So let's meet up again in about 10 or so. Yeah.
What I was trying to ask you earlier was like, what'd you get for number 4? First problem, the very first section.
Well, if you eliminate, yes. Keep all 7 columns. My question.
Did you just augment the matrix?
So,
Oh, I didn't augment it. I started doing the ERs. See if it has a pivot or free variables. But I am on the right track other than beginning. Anyway, you don't even have to do that. Why? Because for 4, yeah, there's 3 vectors. You did the K and the N. What do you mean? Remember the K and the N? Oh, I see.
I thought you saw it, but you run it as Das war irgendwie mal Dynamismus. Before no, obviously, no, I'm not thinking like that. I'm fast, though. I'm saying like,
And that's the potential, wasn't it?
All right, everybody, I think I might go ahead and pick things up for you again here. If we could gather back up again at this point. Yeah, so I hope that I have got you guys in pretty good shape on the homework for tonight. Again, if there's anything else you wanted to talk about, just stop by my office, either in person or in Zoom, and I'll do my best to help you out. I know I'm giving you a lot of assignments here, but I am trying to help you out with a lot of the problems in class. So all you have to do is kind of write them down, make sure you understand what you're doing. I want to take just a quick minute now and change gears completely and talk about what was on the video and take it a little bit from there. So this is in chapter 5. The idea, and I'm not going to regurgitate the whole video again, but the whole idea here is that if you look at a vector space as a mathematical framework, it is a purely algebraic object. There's addition, there's scalar multiplication, and there's then a bunch of rules that are all just algebra rules that you are familiar with from, well, ever since you were doing math. But there's nothing else to it besides that. But then we learned that two of the most natural vector spaces are just R2 and R3. Those are both vector spaces, and those are a lot more than just an algebraic object, right? They are a lot more than just algebra. And in fact, you spent all of calculus solving problems in R2 and R3, and probably half the time you were drawing pictures to understand what was going on. There was a geometry behind it. So those are vector spaces that are not just purely algebraic in nature, but there's actually some geometric insights. So what this is an attempt to do in chapter 5 here for this class is to say, look, let's take our vector spaces, which are algebraic in nature, and let's equip them. Let's add on some structure to them that will allow us to talk about geometry. And that structure is this inner product. Okay, so in the video, I talked an awful lot about it. Basically, the idea is you're going to take two vectors from whatever V is, and you're going to form their inner product and come up with a number. That should sound familiar from calculus, because we've done the standard dot product idea in calculus, where you take two vectors in R2 or R3 and you dot them together and come up with a number. So this is, again, not any foreign idea. This is well motivated by the dot product that you've all seen before. And in fact, what we have done here is created a set of axioms for this inner product that are exactly intended to model the same exact axioms for the dot product. So you go through the dot product, you say, oh, if I dot a vector with itself, it's always at least 0. The only way it could be equal to 0 is if I started with the 0 vector. By the way, this is one axiom that sort of has two parts to it. You have to kind of keep track of both of those. They're both important to think about. So when you're dotting a vector with itself, of course, you get some number, but specifically here, if it's the same vector with itself, that inner product should be at least 0, should not be negative. Okay, and that would be true for the dot product, for example. Doesn't matter what order you dot the two vectors together in. V dot W is the same as W dot V. Okay, if I have a constant inside of one of my vectors, I can factor it out, right? Or if I'm adding two vectors together in an inner product, I can split those inner products apart, right? So these are just axioms that are adopted from the rules of a dot product that you're already familiar with. And I'm going to stop calling it a dot product, though, and start referring to it more abstractly as an inner product, right? So the inner product of two vectors is somehow taking two vectors and spitting out a number. It's really what the idea is. And there's certain properties that those numbers have to satisfy, which are listed in these axioms. Do be sure that you make a flashcard with these axioms on it. I want you to know these axioms. I might ask you to tell me these axioms at some point, so, or to check these axioms. So be sure that you are kind of working on learning those. I know we just watched it over the weekend for the first time, but the sooner you kind of learn those axioms, the better. With this inner product apparatus in our hands, we can then do some geometric ideas. We can talk about the norm or the length or the magnitude of a vector. It's literally just the square root of the inner product of a vector with itself. That's definition. That's the definition of the norm or the length or the magnitude of a vector. Notice that we are taking the square root of something that has to be at least 0. The first axiom forces us to be looking at a positive number under this radical. So you don't have to worry about square roots of negative numbers here, because there won't be a negative number under that square root. And then if I'm given 2 vectors, we can define the angle between them. And again, we do this just completely motivated by how we do it for vectors in R3 using a dot product, right? You probably have all seen this equation before in calculus. For the angle between 2 vectors in R3, we're now going to make this our definition for the angle between 2 vectors in any universe that we're working in. So we can find the angle between 2 polynomials, or the angle between 2 matrices, or the angle between 2 functions, right? Whatever kind of objects or vectors we have, we can try to endow it with this inner product and then use that inner product to answer these kinds of questions. So you'll see on Thursday's homework, there's going to be a couple problems like that where they say, well, what's the angle between x squared and x cubed? Something like that, right? So you can actually do stuff like that in an inner product space. So this is just kind of a quick little summary of what was in the video. Now, in the video, I verified these axioms for a couple of examples. The 2 most important examples, so the 2 best examples of this material here that everybody would want to, if you could only know 2 examples, they would be the 2 that I'm about to write down. The first one is in the vector space Rn. We could use the inner product, which would be, let's just use the vectors A vector and B vector here. We could just literally do the usual dot product. A1, B1 plus A2, B2 plus dot, dot, dot plus AN, BN. So you could literally just dot the components of the vectors together. And that is basically the dot product. Okay. So in the video that you guys watched for me over the weekend, I actually checked all 4 axioms for that example. This is the #1 example of a inner product. It's just your usual dot product. Now, I agree that if n is 4 or more, we can't really visualize a picture of it in our head anymore. We're working in a dimension that's too high to actually think about visually what the vectors would be, but we are still going to persist in talking about the lengths of those vectors and the angles between those vectors. All of this will still make sense once I have an inner product in my hands, right? So I can do that. That's the first of the really good examples. The second one that is super important, especially for applied mathematicians and especially for application-oriented people, is to work in the vector space of calculus functions defined on some interval from A to B. So I'm going to denote that as C of AB. Back when I was first introducing vector spaces, I think I used C of I for some interval. Let's just imagine that that's my interval. And then if we took 2 vectors here, I'm going to call them F and G this time. These are just 2 calculus functions. I can take 2 functions and spit out a number by simply doing, and this one was also in the video, the integral from a to b of f of x, g of x, dx. That would be a great example of an inner product as well. And in the video, I also checked the axioms for this example. So you guys have already spent some time on this, I think, kind of looking at this idea. So this one is very important in functional analysis and applied mathematics. The first one is sort of important everywhere, right? The standard dot product. So they're both really, really important. Okay, any questions so far? One of the things you're going to be doing on Thursday's homework is the questions are going to give you a proposed inner product and ask you whether it really satisfies the axioms or not. I'm just going to remind you, I'm sure I mentioned this in the video, that the first axiom is a good one to look at first, because sometimes when things go wrong, it's this first axiom that doesn't work. So you could end up getting a negative number if they give you a bad formula. So kind of be on the lookout for something like that. So they might give you a proposal and just ask you, is it going to be an inner product or not? If so, verify the axioms. If not, this game works kind of like it did for subspaces. If you find even one axiom that fails to hold, such as the first one, often, then it's already game over. Okay? It's already game over. If you find something that fails in this list, you can stop and say, nope, it's not a valid inner product. I can't use it to do my geometry ideas. Okay, let's just do one more. I know I did a couple of those in the video that you watched, but let's just practice on one more maybe. Just to feel a little bit better about this. I'll give you a different one than what was in the video. So let's say that V is P2 of R. So these are, polynomials of degree 2 or less. And then let's take our inner product. So I'm going to define the inner product of ax squared plus bx plus c with dx squared plus ex plus f. I'm just going to set this up. And let's suppose that I define this to be a times d. So we just take the x squared coefficients. And then so that, at least on the surface of it, seems reasonable. I take two polynomials, I take their inner product by spitting out this number. And this would be a number. So at least in that sense, it all makes sense. But the question is, does it satisfy the axioms? So is this a valid inner product? That would be the question that we would want to try to answer. And so, like I said, the best thing to do here is really, I think, start from the top of the list here and just start working our way down. I promise on Thursday's homework, there might only be one problem where you actually have to go through all 4 axioms. Most of the time, you can stop a little bit short. So let's just check these axioms. If I take the inner product of a vector with itself, then that's going to look like this, right? Ax squared plus bx plus c, inner product with ax squared plus bx plus c. And that's going to be equal to a squared, right? If I just have the same polynomial in both slots here, that would just look like a squared at the end of the day. Is that always greater than or equal to 0? Okay, I'm just looking here. The requirement of the axiom is it has to be greater than or equal to 0. Well, if I look at a squared, does everybody see where I'm getting that, by the way? That's just the a times the d, right? So here it's a times a squared. Yep, that's greater than or equal to 0. But there's a second part to that first axiom that I don't want to neglect, which is that supposedly the only way we can get 0 out of this is if we use the 0 vector itself. And what do you think about that part? Audrey?
I have a question.
Oh, okay. Go ahead. Let's take your question first. Let everybody think about that.
With the AD, so it's kind of like, it's not just a product, but it's also you can assign A to the first vector to be the second head, right? Like the first vector equals A. and the second-
You have these vectors in your hands first, and then you're spitting out the numbers. We're not reverse engineering this, so I'm not starting over here and looking at this and saying, oh, the A goes over there and the B goes over there. It's you start here. I'm just giving you this formula,
Okay.
right? And so you just take the leading coefficients of the two polynomials and just multiply them together. That's my rule.
Oh, I see. Kind of like the form, I guess.
Yeah, it's just a formula. I'm basically giving you this formula. By the way, I mentioned in the video, I think, that I have to give you the inner product formula for anything I ask you. If I ask you for the angle between two vectors, if I ask you for the length of a vector, if I ask you any of the other things we're going to do in chapter 5, we have to have an inner product formula given to us. So this has to be the starting point. What is the formula, right? That we're supposed to work with. If I don't give you the formula, then the question doesn't make any sense. And so you'd be scratching your head saying, what's he talking about? Right? There's just one exception to that. There's one situation where I maybe don't have to always give you the formula. Do you remember what that is? For Rn, if I don't give you a formula, you should just assume that it's this regular standard dot product. Okay, so in that case, yeah, you might not have the formula, but in any other universe, such as P2 of R, I have to give you the formula, which I have done, and then we kind of go from there to continue. Okay, getting back though to this first axiom, there's a second part to the axiom. Do you think that the only way that I could get 0 out of that formula would be if I was plugging in the 0 polynomial to begin with? Or would there be a way to make a polynomial that's not 0, but whose inner product with itself is 0? Blake?
When we're talking about this axiom, it's still in the context of the 12 vectors.
Yes.
Okay.
Yes, exactly. Does anybody think they could make a vector that's not just the 0 vector, at which when you inner product with itself gives you 0? Well, if I'm going to get 0 out of this as an answer, what do you know about A and D? They're going to be 0, right? Could you make a polynomial where A or D or both was 0? I think so. There's nothing that says that this has to actually be a full-blown quadratic polynomial, right? What if I took, I don't know, 5x plus 9? And I take the inner product of 5x plus 9 with itself, right? According to this, the A value and the D value are both 0. There is no x squared term here. So this is equal to 0. But of course, 5x plus 9 is not the 0 vector, right? In P2 of R, this would not be the 0 vector. I literally just made this up. I just thought of my favorite polynomial here. As long as there is a missing x squared term, as long as the x squared is not part of that choice that you've made, then you have a non-zero vector. This is V, right? That's not 0, and yet the inner product of that vector with itself was 0, according to this formula. So it's a bad formula. The answer here is no. Axiom A fails. And we can stop. It's game over at this point. Right? It's not going to be a inner product. Yeah, Blake.
Is it 0 because there's no x squared?
Exactly. Yeah, I mean, this is really 0x squared plus 5x plus 9 and 0x squared plus 5x plus 9. And so the A value is 0. And of course, right there's the A value. So you get into trouble on the right-hand side of the formula. Yeah, Nathan.
So can you assume that for any like polynomial, it would need to, or in the definition, it would need to have all of them?
Yes, it would need to have all of the letters, A, B, C, D, E, F, right? They should all be there in order for this to make sense. Okay, yeah, that's a really good assumption. That is true. Just because all the letters are there doesn't mean it's gonna work. But at a bare minimum, you would expect to see them all there. Yeah, that's a great point. Okay, well, on Thursday, we'll practice this some more because there's gonna be some homework on Thursday that's related to these kind of questions. And I might have some more for you. I wanted to show you another example. I'll call this maybe a warm-up here of something else that you can do once you have an inner product in your hands. Just come over this way to show you here. Let's just say that I told you that I have a vector v whose norm is 2. And then I have another vector w whose norm is 5. And then I have the inner product of those vectors, let's say v and w, the inner product is 7. So if we know those things, I could ask you to do something like this. This is a standard type of question, and you'll see some of this in the homework as well. What if I ask you to calculate the inner product of, let's say, 3v plus 2w, inner product with v minus 4w? Let's just ask, it's making something up again here. Let's see if we can answer this question. And then we'll give a little quick solution here. So this is to be interpreted very abstractly. Notice I didn't even give you the vector space that I'm working in. I also didn't really tell you what v and w look like. All we know is that, well, we must be in an inner product space, and we know the length of v, we know the length of w, and we know the inner product of the two. By the way, just with this given information, we could find the angle between those vectors, because notice that we find the cosine of theta, those are exactly the values you need. That's not what I'm asking for here, but the stuff I circled in blue would be good enough for us to find the angle as well. But I just want to calculate this thing. Does anybody have an idea how I'm going to do that? Yeah, Audrey?
There's a formula for like 1 over the inner product times the inner product times 1 over the norm or something of both multiplying.
That sounds almost like what this is. That's
right there.
That's okay. Good point. That's definitely true. Was there another again? Alex?
It works backwards, like equation, so we know the magnitude, the norm of heat, figure out what you're expecting. That is going to come into this. You're absolutely right. We could actually figure out the inner product of v with itself and the inner product of w with itself, and we are actually going to want to do that in just a minute, because actually what we really are going to do here, guys, is we're going to take this expression and more or less FOIL it out. Why can I do that? That's actually because of these axioms right here. And in fact, one of the reasons I like this type of problem is that it forces me to remember the axioms. A lot of times you can sidestep the axioms in some of the later stuff we're going to do, but I like to keep that in the forefront of people's minds. So you see, like, I could think of this as like v1 plus v2. v1 plus v2 times something else, right? Or inner product with something else. So I can split this up, right? So by axiom, I'm going to just go straight into it here, guys. By axiom D, I can write this as the inner product of 3v with v minus 4w plus 2w, inner product of 2w with v minus 4w. So I could definitely break that apart like so. And then I think in my video, I also explained that you can do the same splitting up in the second slot. Right, so is everybody following what I'm doing here? This is like the V1 and the V2. You're adding them together, and I'm just splitting it into 2 parts. Here's the V1 part, here's the V2 part. I get these 2 terms. But I also want to split up the second slot. I don't have that listed over here, but in the video that you watched, I think I showed how you can actually make that property
apply in the second slot as well. So I can actually go another round here. Let me just call this D prime. It's really axiom D, but applied in the second slot. So 3V with V minus inner product of 3V with 4W. Okay, and then I'm going to do the same thing here. The inner product of 2W with V, and then minus the inner product of 2W with 4W. Yeah, so I can do all of that. I can do all of that. Okay. Awesome. And now I also have this axiom C that allows me to pull constants out. So I notice here in these terms, I have constants that are sitting there. So you can factor them out. And you can actually do it out of either component here, the first slot or the second slot. So like this first one, I'm going to use axiom C here. Axiom C, I'm going to pull the 3 out. So this is going to give me 3 times the inner product of V with itself. And then minus, here I have a 3 and a 4, and I want to pull both of those out. So I'll pull out both the 3 and the 4. So that's 12 times the inner product of V with W. And then plus 2 times the inner product of W with V. And then minus, I guess it would be 8 times the inner product of W with itself. So you can break it into all of those terms, you see. And using the norm definition, so now we're going to get to the point that I think Alex was making, is that, so I want to know the inner product of V with itself. Keep in mind that that's just the norm of V squared. If you square this formula on both sides, the norm of V squared is just the inner product of a vector with itself without the radical. So if I don't have a radical on it, just square both sides, I'll get the norm of V squared. All right, and then I have minus 12 times the inner product of V with W. And then I have plus 2 times the inner product of W with V. And then minus 8 times, well, this would be the norm of W squared. It's going to look something like that. Everybody with me? I'm just using the axioms of the inner product to kind of simplify this expression here. Alex?
Could you use the B axiom for the second, or like for the third term, and just combine the second?
That's exactly what I'm going to do. Yeah, you might have noticed this is the inner product of V with W. It's literally the same as the inner product of W with V, right? They're both the same. So these two are combinable. You can combine them together. But I'm just going to go ahead and plug numbers in now. 3 times the norm of V, which is 2 squared, minus 12 times 7, plus 2 times 7, and then minus 8 times the norm of W, which was 5 squared. I just start plugging all the values in, and now I just have to calculate everything here. 3 times 4, that's 12, right? This is actually minus 70 here in the middle, right? And then minus 25 times 8, I think is 200. Last term should be 200. And so what is that, negative 258? I think that should be right. Negative 258. There's nothing wrong, by the way, with getting a negative answer if the two vectors were not the same to begin with. The only time that our axiom would require us to get a positive answer is if it was the same vector in both slots. And here I don't have that. I have 2 different vectors that I started with. And I'll just calculate their inner product, and I got negative 258. So, just with this information, I could actually ask you to find the angle. I'm just dreaming up questions right now. I could ask you to find the angle between these 2 vectors. So we've already found their inner product, negative 258 on top, and we just have to divide by their norms. And you'd have the answer. So, okay. Questions on that example? People feeling okay? just 5 minutes to go. You know, the rest of chapter 5 is totally computational. Question?
Run through the major site.
Just think of it as a plus with a -4. So, or just plus a negative. It just pulls out. We can talk about it later. Yeah. Let's take just a minute. I just have only 5 minutes. The rest of this chapter is very computational. Like once you have these axioms down and you're working with them pretty smoothly, most of the rest of this chapter isn't too bad. Let me just take a quick stab at the start of this next section on 5.2. We won't get very far into this, but there's not much to say here. This is just going to be about something called orthogonal vectors. So a quick little talk, and I'll make a definition here for you to kind of kick things off. Mostly just going to write down a couple of definitions. V and W, two vectors V and W. These are orthogonal. Does anybody know what the word orthogonal means? Perpendicular to each other. So what would the angle between them be? 90 degrees, right? 90 degrees would be perpendicular. If theta is 90, what is the cosine of 90? 0. So if this fraction is supposed to be equal to 0, that just tells me that that numerator should be 0. That's the definition. So we're just going to say that V and W are orthogonal if the inner product of those two vectors is 0. Very, very simple. And then just to follow that up with one more definition here, if I have an entire set of vectors, let's call it capital S, consisting of, let's say, V1 and then V2 and ... up to Vn, this entire set is orthogonal if the inner product of any two of them, so let's say Vi inner product with Vj, this should be 0 for all I not equal to j. And then if in addition, so I'm going to add a little bit more here. If in addition, the norm of each of those V sub i's is 1, so that would be for all I. So if in addition, every one of my vectors is a unit vector, that's a unit vector, right? You might remember from the video. Any vector of length 1 is a unit vector. Then we call S orthonormal. So an orthonormal set is just, it's just an orthogonal set that also happens to be consisting of unit vectors. Okay, so it's pretty simple. Let me just do a quick example and then we'll call it a day here. Let's just take S. I'm going to give you some vectors here. Let's just do something in R4 for today, and then maybe on Thursday I'll do a more interesting vector space. So let's just take the vector 3, 1, 5, 2. And then I'll take the vectors 0, 6, -2, 2. And then I'll take the vector -2, 3, 3, and -6. And I just want to ask, is S orthogonal? We'll start with orthogonal, and then if I have enough time, we'll look at the orthonormal issue as well. It's pretty easy though. Could do these pretty quickly. Notice that I did not give you an inner product to work with here. It wasn't provided to us, so what should we assume? It's that standard dot product on R4, right? So we're just going to do the usual dot product. Exactly. And I need to do that if I want to check orthogonality here. I would label these vectors, guys. The first one maybe is V1, the second one is V2, and the third one is V3. And all I've got to do, I'll just do it right here, is for my solution now, is I'm going to take the inner product of V1 with V2. And that just literally means that I'm going to dot these two together. So 3 times, I'll just write it out, 3 times 0 plus 1 times 6 plus 5 times -2, which is -10, plus 2 times 2, which is 4. That does equal 0. Right, so we can check that. And then I can do the inner product of V1 with V3. I have to check every pair, right? I have to like, this is supposed to be for all I not equal to j. So I have to check like every combination. So I take the first vector and I dot it with the third vector. 3 times -2 is -6. 1 times 3 is 3. 5 times 3 is 15. And 2 times -6 is -12. We look at all of those numbers, we add them all up, and sure enough, that does equal 0. Okay, and then finally, I would have to do the inner product of V2 with V3. This is the last combination I have to do. So the second one, inner product with the third one, I have a 0. And then 6 times 3 is 18. And then -2 times 3 is -6. And then 2 times -6 is -12. And sure enough, that also equals 0. And so then the answer becomes yes. These vectors are orthogonal. Blake?
If any of the combinations of the vectors are 0.
Then it's game over and you can stop. You can stop. Real quick, are these vectors going to be orthonormal? It's just we're almost done. This only takes 30 seconds. Would all of these vectors be unit vectors? I don't think so. Okay, let's not make a big deal out of this. If I take the norm of the first vector, for example, right? Just take the first one. You can choose any of them, but if I pick the first one, this is the square root of, right, the inner product of the first vector with itself. Well, that would be 3 squared plus 1 squared plus 5 squared plus 2 squared. That is not going to equal 1. That's going to be the square root of something. Did I write it down? I didn't even write it down. Make me figure it out. 39? Square root of 39. Okay, it's not equal to 1. Do I have to go on? No. If there's even one vector that's not a unit vector, it's game over. So the answer here is no. Would we have had a way to make it into a orthonormal set though? Yes, by doing what? Making them all into unit vectors. You can always normalize the vectors. I think I talked about that in my video. So, Blake, come on up when we're done. Guys, that's it for today. I think I'm happy with that. Hope this makes sense. Stop by my office if I can give you a hand with anything on the homework, either for today or for Thursday. And I will see you on Thursday at the latest. Thanks for being here today.